Bonjour, bienvenue à Speaking from Ignorance. Je suis Daniel, je suis doctorat de astronomie.
Okay. Hi.
Oui.
Yeah, welcome to Speaking from Ignorance for all
I
of
just
you
said that.
non-French
What are you
speakers.
talking about?
We're joined today by Sam Morell.
Hello,
Say
everyone.
Hi, Sam.
Hello.
Who is he's now a doctor in astronomy as well.
I am, yes.
Yes, at the University of Exeter. But we'll get on to that. For the time being, Daniel's already introduced himself. I'm Sid. I'm a PhD candidate in astrophysics at the University of Heidelberg in Germany.
I am Jacque. I am a charity sector worker and a social mobility advocate.
And I believe we're missing someone.
Yes, our illustrious chameleon-like actor has hidden himself in the city of London. If
Oh
you
no,
find
he's
him,
pretending to be the guest.
Yeah. If you do find him, send us a picture.
I mean, people could probably do that.
He has given away a lot of his information. You know, you could probably just go to his house at this point.
His
We do
address
not
is
condone
public
stalking,
knowledge.
by the way. We do not condone
Yeah.
stalking.
I mean, please do. Feel free.
What? No,
It's his own fault.
that's
really.
not good advice. That's terrible.
Find
He
us,
needs to
really.
learn what security means.
Come say
What,
hi.
by being stalked? Criminal behaviour should not be a teaching exercise.
On that note, Sam, do you want to introduce yourself?
Yes, hello everyone. I am now Dr. Sam Morell. I'm an astrophysicist, and I'm currently working at the University of Exeter. So, I know you all because you were formerly of said prestigious university, right?
Yes.
Indeed, yeah.
All of us did our undergrad in physics there. Minus Holmes. But again, he's not here.
I tormented the crap out of all of you for every
Yeah.
waking moment, and it was fun.
I mean, some people have mentors. Others have tormentors.
Oh, I like that. I'm going to use that in the future. Oh, no, I'm not a mentor. I'm a tormentor.
Yeah. Sam, what did you do your PhD in, specifically?
Astronomy? No, I'm joking. I did, basically, my PhD thesis was on, and it sounds really boring, but it's genuinely not that dull. I did my PhD thesis on measuring the sizes of stars.
Forgive me, because I know nothing about science. But how can
As
you
the
work
physicist-
Jacque, you have a master's.
It's been a year since he's
How can you
utilised
work
that
out
master's degree.
how large a star is?
Okay, so I'll give you the executive summary for the executive in the room. Okay.
Thank you.
So basically, we use a technique called SED fitting, and an SED is something called a spectral energy distribution. If you basically take all the light that comes from a star and you lay it out on a graph that breaks it down into the wavelengths that it's coming in at, so the frequency of the light, versus the amount of that light that comes in, or the energy of the light, you end up having a very, very distinctive shape to it that is incredibly dependent on the temperature of the star. So stars have a load of, as Sid will tell you, stars have a load of chemicals in them that give off, that either absorb things, absorb light, or emit light. But underneath all of that absorption and emission is just a black body function, which is dictated by the temperature on the very outer layers of the star. So our technique uses that black body function combined with the very, very deep and distinctive spectral features that come from the stellar atmosphere to work out what temperature it is. So we have a load of grids of models. So we use those models to figure out the shape of that SED function to give you the temperature. And then using really, really high precision parallax data from a mission called Gaia, which I'm sure some of you have heard of. Yeah, Sid is. Oh, I'm down.
Yeah.
Represent.
Even though I don't
Represent.
use it, it's very hyped. Gaia is pretty good.
So Gaia is awesome. Like, Gaia is incredible. I love Gaia so much.
Who is this dude?
But But yeah, we can use parallaxes from Gaia, which is basically if you move your head back and forth and look at objects in front of you, the objects that are further away will move less than the objects that are closer. And that's what Gaia is doing. It's orbiting the sun behind the Earth, and it's looking at faraway stars, and it's working out incredibly accurately what their parallax is, which from that you can work out what their distance is to an incredibly, unprecedentedly accurate precision.
Like,
Right,
maths
so
is pretty cool when it works.
So it's like being in a moving train and having for sort of like close cars near you move by really, really quickly, but for sort of trees really far away just move really, really slowly. So you
Exactly.
And then
measure that
you're
sort of
asking
movement.
how far are the trees, how far are the cars, how far is the meadow behind the trees, that sort of stuff.
Yeah.
Right.
But imagine you can see that like stupidly precisely, like incredibly precisely. Like you can see leaves miles and miles. And I think it was seeing a footprint on the moon is how precise that the distance of a footprint on the moon. Or I think it was 3 centimeters on the moon.
They should hire this Gaia
That's a
guy in
small
next
foot.
Avengers. Should replace Hawkeye.
Yeah. But yeah, we can use those distance measurements and to work out, based on how bright the star appears to us, its luminosity. So
What does that mean, sorry? Is that
So
is that
its
just brightness?
yeah, its luminosity is basically its total brightness, how much light it gives off in total across every wavelength. Using the luminosity of the star from the distance and the SED fitting and the temperature from the shape of the SED, we can then put those into one of the most fundamental equations in all of astrophysics. Anybody?
I can't remember what it's called, but the L equals T, or L proportional to T to the 4.
That's the one. L equals 4 pi
Yeah.
r squared sigma Tef to the 4. Yeah.
Yeah,
Tef
that one.
being effective
The
temperature.
Stefan Boltzmann law,
That's the one.
Yep, that's it. Stefan Boltzmann.
That's
yeah.
the one.
which
So
tells you that the luminosity goes as the 4th power of the effective temperature of the star.
Exactly.
That's what I
And
said, yeah.
we've come full circle. That's a very long-winded answer to Jacques' question.
Yeah,
You look at
because
them.
You look at them. You look at the luminosity. You look at the shape of the curve, which is dictated by the Stefan Boltzmann. Stefan Boltzmann law falls out of that black body, and then you can use all that information that you get to figure out its radius, and we can get the radius to about better than 2%, which is incredible considering that the state of the art is somewhere around 2.4, 2.5%.
Okay, and why does knowing the radius of stars matter?
Well, it matters because two main reasons. So at the moment, I'm kind of straddling two different fields of astrophysics with this work. So I'm straddling stellar evolution. So if you can figure out what radius a star should be, you have an incredibly powerful idea of what's going on in the interior of the star at that particular point in its lifetime, because you know how big it is. Because stars
Since you know how big it is, you've used how bright it is to get that information as well. So you also know that.
Yeah.
So it's almost like you have these 2 points. So you're zeroing in on this grid of potential stars. So you all know almost exactly what kind of star it is.
Exactly, yeah. And given that most of a star's evolution in its early lifetime is dictated by gravity, knowing how big that is, knowing how big that shell of gravity is very useful. The other thing which is kind of useful is exoplanet science. So
yeah.
all of our information about the sizes of exoplanets, for example, is highly, and I mean highly, dependent on how good the measurement of the star is. Because all of the measurements that you make of an exoplanet orbiting a star, at the moment at very least, are taken relative to the star's measurement. So, for example, you can only really measure the radius of an exoplanet as a ratio of its radius to the star's radius. So if your radius is wrong to say 10%, then that's putting a very hard limit on how well you know the planet that you're studying. And even like if you can measure that to 10%, that puts like a 30% limit on the density of the planet, which you kind of need to know if you want to figure out
what kind of planet it is.
Exactly. You don't know what kind of planet it is. It could be an Earth-like planet. It could be a mini Neptune. You know, you've got a large uncertainty in those measurements. So that's kind of the two things that you really want to know the radius of the star.
Yeah. Thanks for going into your PhD thesis. But I think a project that, you know, Jacque and I know very well is something called XRT-C, which you basically spearheaded and commandeered for 5-6 years. At least as long as we were there, and you know, 1 year here and before and after Jacque and I left.
Yeah.
What's XRT-C, Sam?
What's XRT-C? It's a good question. I'm not even sure I know at this point. So XRT-C stands for, and here's another fantastic astronomy acronym for you folks: Exeter Radio Telescope at Caradon. And essentially, this was a project that was started way back in 2011, 2012 by Freya Aldred, who was a student at Exeter, and I think she's at the Met Office now, and Dr. Damien Rumble now, who was a PhD student at the time. And what it was is, or what it is even, is a project, a completely student-run project, to build and run a radio telescope, and not just a cheap amateur grade radio telescope, like a professional research grade radio telescope.
What is a radio telescope?
Okay, right. So I'm sure that we all know roughly what an optical telescope looks like. Some kind of tube, probably with a mirror in it.
One of those normie telescopes.
Pardon?
So one of those normie telescopes.
One of those normie pleb tier telescopes, yeah.
You look at visible light. Oh.
Ew! You use mirrors. You can get smudges on them. That's disgusting.
Well, telescopes are just a way for us to look at any wavelength of light.
Yes.
Just the way they're built is just tailored to a specific wavelength.
Yeah.
So
yeah, as Sid said, telescopes are just a way of focusing light and magnifying it in some way that you can see things far away. Now, we're all used to, say, optical telescopes, which use light that we can see with our eyes. Other telescopes use ultraviolet light, which is way higher energy than we can see. Other telescopes see infrared, and there's a whole spectrum there of electromagnetic radiation. If you go down far enough to low energy light, you get to the radio regime. And so light is, its energy is dictated by its wavelength, right? So light that we could see with our eyes is, say, 500 nanometers is roughly the average. It's kind of a normal...
What's a nanometer? No.
What's a nanometer?
Yeah. But I think it's important to illustrate just the scale of wavelengths here. So 500 nanometers, 10 to the minus 9 meters.
Yeah.
So
a billionth of a meter.
A billionth of a meter, yeah. So that's the kind of average wavelength of the light from the sun is, say, a billionth of a meter. Or 5 billionths of a meter.
Yeah, that's how, if you took a wave, one single photon, and you said, how wide is it? 1 billionth of a meter.
It's tiny!
Yeah.
If you look at radio wavelengths, in particular the radio wavelengths that XRT-C observes, that's on a much more human understandable scale. That's 12 centimeters, which is much, much, much lower energy than the light that we can see.
It's it's legitimately you could put your hands out and feel 12 centimeters. So
it's a ruler, right?
It's like half a ruler, yeah.
Half a ruler, 12 inches.
Oh, right, okay.
Well, it depends how long your ruler
so
is.
rulers.
I mean, I only use 12 centimeter rulers.
This is my 12 centimeter ruler. Yeah.
But yeah, say picture a ruler or a half a long ruler. That's roughly the size you're looking at.
Yeah, so that's the wavelength we're looking at. But a radio telescope itself, if I understand correctly, looks more like a satellite dish than a conventional telescope.
It does indeed, yeah.
Yeah.
So you might say, well, yeah, how does it work then? So in normal telescopes, you tend to have mirrors that reflect the light, right? And they work because the distance between the atoms or the molecules that make up that mirror are much smaller than the wavelengths of light itself. So it's basically it doesn't really interact with them. It acts as a reflecting surface. And so you look at a radio telescope like XRT-C and look and see it's got a mesh dish on it. You're like, well, how on earth does that reflect anything? It's got holes in it. And it's just because the mesh in the dish is, as with a normal mirror, is much smaller than the wavelengths of the light that it's reflecting. Say these holes are, say, 1 to 2 centimeters wide, and it's reflecting 12 centimeter radiation.
So
Quickly interject here, Sam, for a quick fact check. What's up with the 21 centimeter line? Was that the one on campus that's 21 centimeters?
No, they're both 21 centimeters.
Okay. Why is it 12 centimeter wave?
Sorry, 21 centimeter.
Okay, so instead of 12, we should be saying 21.
We should be saying 21 centimeter.
Why 21 centimeters? Why is that important?
Asking the easy questions, as always, Sid.
Yeah,
So,
that's my job.
the 21 centimeter emission corresponds to a very particular energy level in hydrogen, in the hydrogen atom. In a neutral hydrogen atom floating out in space, you have a proton and an electron. One of the numbers of protons and electrons, one of the just kind of the quantum numbers that dictate what state they're in, is something called their spin. The spin doesn't correspond to anything rotational, like it's not actually spinning.
It's a bad name.
It's a bad name, but the mathematics...
But we call it this thing now.
Yeah, but all you need to know is that the mathematics for spin look like an angular momentum as far as quantum mechanics is concerned, which is why it's called the spin. Like, it's a terrible name for anybody else.
But kind of works.
But it kind of works mathematically. So
And we're stuck with it now.
yeah, we're stuck with it. We can't do anything about it. But all you need to know is that it can be in 2 states, spin up or spin down. Now, both the proton and the electron in a hydrogen atom can be in a spin up or spin down state. Because spin is determined by magnetism, if you have both in the same direction, i.e. both the electron and the proton spin up or spin down, they will be in a slightly less energetically favorable state than if they're opposite, because the magnetic fields don't want to be facing in the same direction. So it is very, very, very slightly preferable, as far as nature is concerned, for them to be opposites. Either one spin up and spin down, or the other way around. So as we all know, nature loves optimizing energy. That's why, say, bubbles are spherical, because it's the most energetically favorable shape for a bubble
you
to
sound
be.
just like Brian Cox right now.
And that is also why the Earth is also roughly spherical, or an ovate
I can't
spheroid.
believe we've got Brian Cox on the podcast.
And so when I look up at the stars and I look at these wonderful burning balls of gas, so yeah.
So is Brian Cox. I'm sorry about that.
Also, I'm sorry, Brian Cox, for my terrible impression. If you listen to the podcast, which you obviously do.
Definitely does, yeah. He's
Yeah.
the number one
100%,
fan.
yeah.
We do have so many listeners. So. Anyway, sorry.
But yeah,
bubbles.
So nature will always tend to try and make things in the lowest energy state possible. But the problem with this spin flip transition, which is what it's called when they flip from the same way to opposite ways, is it's such a low energy that it's incredibly unlikely to happen. And you can basically, if you hold, say, a single hydrogen atom in isolation in a box somewhere and watch it until it flips, you would probably be waiting for longer than the age of the universe for that to happen. That's how unlikely.
More than 14 billion
More than
years.
14 billion years, yeah. It's called a forbidden transition for that reason. It's incredibly unlikely to happen. But the thing that's in our favor here is that we're not looking at one single hydrogen atom floating in space. We are looking at many, 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 many billions and billions of hydrogen atoms out in space. And the numbers check out that, you have so many more hydrogen atoms than the likelihood of not seeing this line, that the entire galaxy is basically glowing back at us in this radiation.
Yeah, you see it all the time.
We see it all the time. Like, it's literally
And
just
that
a fixture
and the
of
energy
space.
of that transition Its wavelength is 21
12
centimeters.
21
No,
centimeters.
not 12, 21. So, what's up with Caradon Observatory? Why Caradon? Why is Caradon such a good place to look at the sky?
Caradon are basically Ken and Muriel Bennett down in Cornwall. Ken was a nuclear engineer on submarines, I believe, way back in the day, and now he's retired to Cornwall to basically build his own observatory. So they have a really nice setup down there. They have a load of domes with telescopes in them, one of which is our control room now, actually, and they have a lecture theatre down there, and basically their whole thing down in Cornwall is to bring astronomy to Cornish people, to the everyday person, and to do outreach to schools. And they're really committed to involving the community in the wonders of both astronomy and the dark skies of Cornwall. And that's why it's great for optical astronomy down in Cornwall, because they're on the edge of Bodmin Moor. And one of the things that we actually helped do while we were working on the telescope was to help them support their dark sky bid. So thanks to, in part to us, a very small part, I will add, most of the work was done by them, but thanks in part to us, Cornwall and the world now recognises Bodmin Moor as an international dark sky landscape, which means that it's protected kind of by law from light pollution. And because of how remote the observatory is, it's kind of sandwiched between Liskeard and Launceston, I believe. And it's deep in a dish. It's like deep in a valley. Because we're on the side of a valley, it means you don't get any interference from nearby towns and cities and radio emission. So it's ideal for a radio telescope as well, because you don't have any interference from nearby sources of noise.
Another thing that might not be clear to some of our listeners is you can do radio astronomy not just at nighttime, though.
Oh yeah, you can do it. You can do it anytime you want. Yeah,
because because we're looking at not optical wavelengths.
It doesn't matter if the sun's out.
Yeah, but what are the sort of natural things that you should be aware of if you wanted to do radio astronomy yourself?
What do you mean the natural things? Do you mean just like?
Yeah. So when you're setting up your radio telescope, what's the sort of stuff you should avoid? Because in a conventional telescope, it's the sun.
Yeah, I mean, to be fair,
clouds and things that you can see. But
to be fair, unless you're calibrating, you should avoid the sun as well, because the sun does actually give off this 21 centimeter emission. So the sun does give off that. But if you're wanting to do radio astronomy yourself, you should definitely look to avoid all kinds of electronics, all kinds of buildings. You shouldn't point it at the ground. You shouldn't point it near landscapes, because grass gives off 21 centimeter emission. Trees give it off. Buildings give it off. Hey, people give it off. So you want to stay as far away from any kind of thing or source of electronics as possible, because pretty much anything that you get in the beam of your telescope, like in the field of view it has, will add noise to it. Apart from clouds are fine.
Yeah, I think we talked about why 21 centimeters, but why is the hydrogen spin flip transition useful to look at?
So the neutral hydrogen transition is super useful for a number of reasons, but the main reason that we're looking at it for is because, generally speaking, in space, when you look up at it with a normal telescope, you can only see things that are giving off light, or things that are reflecting that light, right? The thing which is really cool about the 21 centimeter emission from hydrogen is it doesn't require a star nearby. All it requires is at some point in the past for that energy level to have been kicked up. And it's so small that that's quite easy to do.
So I guess it's sort of like in space, you can look at things because there's lights everywhere. Like if you had a lamp and you had a bunch of dust around the lamp, in order to see the dust, you have to turn the lamp on. You have to have some light that shines through this dust. But with the 21 centimeter line, it's like the dust itself is giving off light without any sort of lamp. A faint amount of light, like very, very small, but enough that we can see it.
Exactly, yeah. It is its own source of light. It doesn't need anything else to be lighting it up. And it means that you can see structures of galaxies that you couldn't see otherwise because there are no stars there, basically.
I remember, though, doing this actual radio astronomy experiment at Exeter, because I think it's one of the projects that you can do, Q ad for Exeter Uni. No. It's one of the projects you can do in the experimental astrophysics astronomy labs.
Yeah, it's like the third year project.
I think it's second year, right? It's a second year extended experiment. So we spent like 5 weeks with Sam.
You poor
basically
person.
Looking at. We weren't using XRT-C because there is a radio telescope now. I think 2 on the physics building.
Yep, there are 2 now.
The University of Exeter. So we point that
an
one.
Optical telescope.
Yeah, so I remember.
Actually,
yeah, but nobody cares about those.
Oh,
That's the other lab that Sam runs.
I like direct imaging.
No, but I remember using the radio telescope and actually taking measurements, but we had to basically track all around the sky and go in like super early in the morning to track some galactic midplane, I believe, like near galactic center things. But the reason is because the whole galaxy is glowing back at us. You can actually measure this light from the galaxy, and if you know where you're pointing the telescope in terms of galactic coordinates is what they're called, just how we see things in the galaxy. So like galactic latitude and longitude. You can then say, hey, I get this much energy from these coordinates, and you can actually plot out the Milky Way. Like, you can do this experiment. If you did have a radio telescope, you can literally look at the sky and plot out what the Milky Way galaxy looks like.
Yep, that's pretty much what you can do. It's a really cool experiment. If you do this experiment, you'll notice something really, really cool. And that is that as you point your telescope at different parts of the galaxy, the frequency that you observe this light coming in at is ever so slightly different from what you expect. And the reason for that is Doppler shift. So we're all familiar with Doppler shift, right?
Probably not the listeners.
Yeah.
I have no idea.
Explain it for people who don't have a master's degree in physics.
Yeah, okay. Things moving away from you have their wavelength shifted to longer wavelengths or lower energies. Things moving towards you have their wavelengths shifted to shorter wavelengths or higher energies. And that's just because it's moving towards or away from you. The classic example is an ambulance or a fire engine, right? You hear, do you want me to do I don't want to do the demonstration.
Please
I want to do it anyway. If you have it heading towards you and then going away from you as it goes past, it goes, Nina, 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 Nina. And that is Doppler shift in your everyday life. Now, because light is also a wave, it does exactly the same thing. As things come towards you, they get higher frequency. As things go away from you, they get lower frequency. And you can use the frequencies of the light that you observe at different parts of the galaxy to actually figure out how fast the galaxy itself is moving, right? And because you know how
cool.
It is pretty cool. And because you know how fast it's moving, you know what its energy is, and you can balance the imaginary centrifugal force against the centripetal force that's having to hold that material in place, and you can actually figure out what the weight of the galaxy is just from these basic observations of light. And it's really cool. And that's kind of what one of the main objectives of XRT-C is to do, is a group of students being able to actually do that measurement on their own telescope.
Okay, but that would only be that would only be matter, right? Like matter, and not like dark matter, right?
What's dark matter?
So I believe what Jacque means here with matter, and dark matter. Matter is the matter you can see, right? Dark matter
that light interacts.
And light interacts with. Dark matter is the matter that you can't see and light doesn't interact with. I.e.,
95%.
we have no way of seeing it, right? As far as we're concerned, it's not there. The only way that we can actually see it is with this measurement, with actually doing this measurement. and looking at the shape of this rotation curve.
Yeah, because what you see is that the galaxy is a lot heavier. Well, it needs to be a lot heavier than what we see from the light shining back at us for the physics to work.
Yeah.
And why the whole thing doesn't just fly out into infinity.
If you look at so as you go out, you make measurements on the galactic disk as you go outwards. What you actually get is this function of rotation rate of the galaxy as you go further out, as a function of radius in the galaxy, right? And the really weird thing about this is that, as you know, based on what we know galaxies look like, as you go further outward, the speed should fall off because you have all the matter concentrated near the middle with the bulge and, you know, a load of the material inside the center of the galaxy. And it falls off as you go further out, according to what we know. So you would expect that line to fall off, to decrease as you go outwards with radius. But what you actually see is the galaxy rotates as a rigid body. It rotates kind of, when you get past the initial blip upwards in the middle, it pretty much has a constant velocity as you go further out. And that makes
really weird.
Absolutely no sense if given what we know about galaxies. So that's where dark matter comes from, is that rotation curve.
Yeah, which you can see with a radio telescope. See is a strong word. Infer from a radio telescope. You can
infer from a radio telescope, yeah.
Who's joined us from the void of the break? Who's that?
'Tis I, Clemens von Metternich, former Austrian ambassador and 19th century diplomat. No, it's me, using my cunning chameleoid powers of disguise, trained in me 4 years of experience in an acting conservatoire. Yes, 'tis I, Henry Holmes. How are we all?
So depleted. You've clearly had a really rough morning.
Doing pretty well. How about you, Holmes? How are you doing?
Oh, fine. I knew what day it was.
Why are you late this episode?
Late? Surely we're going to edit this so it sounds like I was here first.
What's important is you're here now. We were talking about... we actually talked about dark matter, Holmes. I'm not sure
very, very familiar. Mr. Matter, first name Oliver Dark, lives down the road from me.
One of the lesser known Sherlock Holmes novels.
Yes, it's about his inept actor brother Henry Holmes, who basically stumbles on cases.
Quick recap, though: if you want to check out more about XRT-C, go to the website XRT-C.co.uk, where you have actually really cool videos of people, not me, setting it up. Sam, are you in this video? Are you taking the video? It's tripod. You're probably
I am in that video, yes, and I believe some of you may be in that video as well.
Weirdly, I'm in the video.
I don't think I am, but I think Jacque is.
And that is why that video is not very good. It could have done with some Holmes.
I mean, there's a great way to get work as an actor if you want nobody to see it. It's appear in loads of corporate training videos.
Oh,
this is a step below that. This is outreach video that no one watches.
Like,
they're not even enforced watching in companies.
Oh dear. Well, you know, outreach is always good though. You know, you've got to do it even if you think that nobody's watching it, because on the off chance you do inspire that one person.
But also, the XRT-C is an official national project of UK SEDS, the UK Students for the Exploration and Development of Space. So, official national project here, XRT-C, big boy.
And we won an award for that project.
That's true, we did win an award.
I won't mention.
Yeah, you really can back it up.
I won't mention we were the only people running for the award.
Just mention.
Cut that. Yeah.
But yeah, we won an award. We have a nice
in a hotly
shiny glass
contested
award.
field. You won an award.
Yeah, we won.
Yeah, if you guys are in the UK though, and you know, go to the XRT-C website. If you want to check out some projects near you, definitely check out the UK SEDS website as well, ukseds.org.
Wow, we're plugging a lot of websites today.
Lots of cool stuff. Well, it's a lot of like cool student science that's going on. Sam, we've talked a lot about like astronomy and space science, but we haven't touched upon the true meat and bones of this podcast, which is funk guitar.
Ah, well, yes. I'm glad we're here at long last. Real tennis and funk guitar are the backbones of
That's
this
this podcast right here. But no, more seriously, you are actually a funk guitarist.
Yes, believe it or not, I actually do funk guitar in my spare time.
Tell us more.
As part of...
I play as part of a band called the Soul Traders. Yeah.
Whereabouts do the Soul Traders normally perform?
They don't normally perform, but still, well, especially at the moment. Basically in and around Devon is where we tend to ply our craft.
Devon, lovely county.
So, what do you want to know about Soul Traders then? Because
do you guys have a website?
southernsoultraders.com if you want to go and see.
What kind of soul?
Northern Soul. Believe it or not.
Oh, this band's bigger than I expected.
Oh yeah, there's about 12 people in it at this point. But yeah, I play guitar in said band, and I have played guitar for 18 years. My guitar playing can drink now. Excellent.
Oh wow!
But yeah, no, the band itself I think has been going for 20 years.
Wow. So it's had a few changes in membership.
Yeah, just a few.
Just a few.
Yeah. I think I've been in there now for about 10 years or so.
Serving his time.
And I've played about 100 gigs probably. We average about 9 gigs a year, so not many, but it's good fun.
Yeah, and that's what you want, really, isn't it? If you're not enjoying it, what's the point?
Exactly. Yeah.
Yeah. Especially since you're not a full-time
Oh yeah,
musician.
no. If you're a full-time musician, then maybe you've got to do a few things you don't enjoy.
Maybe 9 gigs a year is not a great
Yeah.
number.
You have been spending a lot of time, getting a PhD. So
Yeah.
Yeah, small thing. Small distraction from playing music, the old PhD.
So what would you say, as a guitarist, distinguishes funk guitar from other styles that people might be more familiar with?
I would describe it as jazz with more groove.
Jazz with more groove.
That's
okay.
That's a pretty good way of
Jazz with
saying
more
it.
correct notes.
You're welcome, guys.
You want to shove those seventh notes in and just grind as much as you can on the strings when you're strumming, right?
Maybe we can pick another style of guitar to contrast it with to make it more
Metal guitar. Yeah.
even.
As in thrash metal. Yeah.
All right, slash metal versus funk. I was thinking more like blues.
Oh, blues. Yeah, that would be a more reasonable comparison. or to just be really odd, shall we go the difference between classical guitar, which will probably be a style the audience will also be unfamiliar with, and funk guitar?
Well, a classical guitar is also a different.
They hold it differently, yeah.
Yeah. But it's also a different instrument than what you would normally use for a funk guitar, which is electric.
Do you find...
Although if you're Corey Wong, that doesn't really seem to stop you. You can do it on anything.
No.
Do you find
No, it doesn't.
acoustic or electrics easier to play?
On the whole, like electric is probably easier to play.
Yeah, I've always found electrics easier to play.
I don't know why, but acoustics, yeah, the acoustics have a higher action, which is like the height between the fretboard and the string, and it makes it a lot harder to fret the actual notes, especially if you have like really thick nylon strings on it.
Yeah.
See,
Use
I
steel
was
strings,
going
kids.
to say the exact opposite, because I think it really depends on like what type of music you're playing. Because if you're trying to play those like really, really like quick riffs, you kind of need like really, really low action to be able to have enough just, I don't know, sustained power to just like keep going.
Or
I
just
think
have really
bar
strong
chords are
fingers.
easier on an electric as well.
Oh yeah, definitely. I
Because
agree with
again,
that.
it's the action. Like, whereas on an acoustic, I'm like, oh no, that sounds horrible. Like,
Yeah, well, I think we can all agree that anything to do with pressing strings down is easier on an electric guitar just by the nature of the electric guitar. The difficulty then comes in, how do you make it sound good? Because there's a lot more... on an acoustic guitar, you have like harmonics and stuff and, projection.
I'll
as your
show you
main
how you make it sound good.
weapon in
You
your
get the
arsenal.
little lever and you go, wow, 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 wow.
The wham bar.
whammy that
Whammy
bar.
Yeah.
After every single chord.
Which is something you don't really hear in funk guitar.
No, you can get away without the bar in funk.
Yeah.
You
You gotta actually be good.
Oh snap!
No, I'm kidding. I've never played funk guitar.
Basically, in funk, your friend is muting. So if you are kind of stopping the string from playing or taking your fingers off in a very strategic way,
quite percussive,
that is your friend.
Yeah,
that's how you get the like
dead notes.
like that. That's how you get the dead notes, as Sid said. Is you very very strategically mute your strings as you're playing them, and you always have to kind of have your plectrum just going up and down like that, just grind it away at those strings.
Just turn your right hand bones into
so it's just straight up and down. It's not like down, down, up, down, like you might use in some other playing styles.
Oh, you can do that.
on the
Yeah,
style,
it depends.
right?
You can kind of, especially if you're like ska is actually quite similar to funk guitar, but you tend to then go chick 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 upwards instead of downwards. So you kind of have to play very rhythmically in ska as well. And actually, I have managed to the. I don't know if my bandmates have noticed this, but I've actually managed to sneak in some ska skanking.
They're going to listen to this now and they're going to go, oh, he's not a purist. Kick him out.
Bastard.
Do you say he's not a purist? He's a funk guitarist. You can't be a purist and a funk guitarist.
I want to be a funk purist. That's what that's what we need to get. Oh wow, that's what we need.
Or a jazz purist.
I am merely a disciple of jazz. Of funk. I'm not a purist. That's the Corey Wong himself is the purist.
I was born in the funk. You merely acquired it.
And Nile Rodgers. Let's not forget Nile Rodgers as well, who is Chic fame.
Do you think possibly one of the links between astrophysics and funk guitar might be the sort of the oft proposed links between mathematics and music?
Yeah, no. Music is incredibly mathematical, and I know a load of physicists actually who are like, I could never play music, and I'm just going. You do realize that all of music is basically just mathematics, right?
Yeah.
So you work your way from root notes, and like, oh, what's an octave? Well, you just double the frequency, and you double the frequency, and you double the frequency. Like, it's all mathematics, and I think
musical notation
people.
is a language, much like mathematics is a language, and I think it's similar in the sense that you can. I can't remember what the word for that sort of language is, but it's where it communicates. Oh God, I've completely lost my thread, but it's a different sort of language from our everyday spoken variant.
It's a purer language. From a more civilized time.
Yes, it's Italian with little dots.
I suppose traditional language communicates both ideas and concepts, right? Whereas musical language is just one of those. It's just sounds.
But the musical language does communicate concepts. It's like musical phrases. They are written for a certain purpose. They embody certain emotions. You can evoke those emotions and tell a story through those collections of notes, forming sentences and paragraphs.
Phrases, yeah.
That's why you call them phrases, yeah.
And there is room for interpretation within music as well. If you look at an instruction like rubato, that somebody's rubato will be different from somebody else's, which is why you rehearse. Because otherwise you go...
The mandolin begs to differ.
No, man, just play jazz.
We're just going for a kind of polyrhythmic, polytonal, kind of soupy mishmash.
I have a video up on my other screen on how to do polyrhythms, because it's something I'm trying to learn right now.
You've been watching too much Snarky Puppy, Sid.
That's true, yeah. Snarky Puppy, another great funk band. I watched their NPR music thing 4 times in about 2 days.
Okay, what funk bands do we like then? So you've got Snarky Puppy, you've got Wolfpack.
I don't know if these other ones count as funk. They're all different genres of jazz, but subsets. There's Moon Hooch, which does cave music, which is kind of funky. Then there's Too Many Zoos, which is very bombastic, but I don't know if it's funk. It's more like acoustic dubstep, and they call it Brass House.
Acoustic dubstep? That sounds so interesting.
Yeah, you should check it out. It's an NYC subway band.
Oh, those guys. Yeah, I know the ones.
Acoustic dubstep. That's...
Yeah.
I think I've seen some.
Yeah, it's got Leo Pellegrino on sax as well.
I'll throw in Ripe to that mix. Ripe are a really cool band. I've
Quite
seen
cool.
a lot from lately. Their debut album is fantastic.
Does Jacob Collier count as funk? I mean,
Sometimes depends on what he's
Jacob
playing.
Collier has transcended from genres. He's just his own
I think he
thing.
counts as music, and then you can just sort of pick everything, and he would probably fit into literally every category.
That is totally true. Like, he has so many different aspects of like world music, especially in his like latest albums. I sound super douchey, so I'm just gonna stop.
I enjoy the idea of transcending genre.
If anyone does, it's Jacob Collier, right?
Interesting.
Yeah, Tame Impala.
Tame Impala are good, yeah. I was going to say, I think we're going off funk quite drastically at the moment.
I like a band called Scary Pockets.
Scary Pockets are great, yeah.
Yeah, thank you guys.
But I actually think there's a lot of like parallels between what we classically think of as scientific mathematical subjects and more artistic ventures. Even in my like normal work, I'm usually trying to find like nice ways to present what I like my results, because there's like they always say it's all about that. It's all about those pictures.
Oh yeah, definitely. And I think the way that you actually kind of a good paper or a good scientific article will be very careful in the way that it crafts its language and its ideas to kind of not force an idea onto you, or to inelegantly force something onto you, but it will try and craft its way of thinking and its English or language towards drawing you to the idea. Like it should be a finely crafted narrative, not a boring, dry
Hodgepodge.
Yeah, you don't want to have
half
to
melted
read
ideas.
a tract or a diatribe or something like that going. And on the because at that point it becomes a little bit too much like I don't know if everyone experienced this, but when you're younger and you're sort of subjected to assemblies where people read bits of the Bible and things like that. And on the fourth day, Jacob came unto the land of Canaan and did make the rain come. And they sacrificed the goats and the pigs and the sheep and the camels and the kangaroos and the ducks and the lesser spotted pink flamingos.
Did you read the same Bible as anybody
I read
else in
the
world?
same Bible as that's actually from the Book of Armaments. It's normally cut. It's they read a bit of it in Monty Python's The Holy Grail. With regards to the Holy Hand Grenade of Antioch.
I just think there's so many parallels between science and, music in particular right now, because I'm doing a lot of music, but just all sorts of art. And it's like you said, Sam, it's very much about, writing a very precisely crafted, persuasive point, but still showing the other side. But you're painting one side of the narrative very clearly and leading your readers to the same conclusion that you came to, and it has to make sense all the way throughout. Sort of like a piece of music, it has to be coherent all the way throughout.
But yeah, I think there's an art there to, as you say, like you can interpret writing as you want, and your real craft here is crafting it in a way that the interpretation is the right. You take, the interpretation that everyone takes away from it is the thing that you want them to. And that's the funny thing about art, is that I think this is the kind of where they diverge a little bit, is that art is almost intentionally quite often left kind of ambiguous so that you can interpret it and read into it in the way that you want to. And I think that is one of the things that's really special about art and about kind of creative pursuits in general, is that you craft something and you get something from crafting that, or you put something into it. And then the person who is kind of viewing or consuming that art can have a completely different interpretation of it. But it's still just as important.
Yes. Yeah.
The different interpretation that you can
I think
pull
the
from
best art does that and manages to stay relevant, which worries me at the moment, being very in sort of the performing arts world, because it's inevitable. Every generation has political art, political theatre. It is as old as politics. But there's very little being produced in the performing arts at the moment that isn't, on some level, a political comment on the current stuff. And the best of that stays around, actually, and becomes something else and becomes something other. Because For example, a lot of Oscar Wilde's plays are actually full of quite subversive political comment for the time, but we don't think of it like that now. We just think of it as light comedy of manners. And hopefully, I think the best examples of our currents... I'm speaking mainly from a performing arts point of view because I'm a bit out of it with the visual arts and things like that. But hopefully that will also manage to ascend to that plane. So once the original context has been lost, it still has some inherent value as art. And as you say, can be interpreted by different people in different generations in different ways.
Yeah, and I think just what you were saying there, I think I was thinking of Bob Dylan in my head for some reason. Like, you know, very, very politically charged messages that were made generations ago at this point, like two generations ago, still listened to this day, and a load of the messages in Bob Dylan's music still kind of ring true. So that's kind of almost transcended time, even though it was written about a very specific thing in history, a very specific point in history, still very relevant to this day, I feel.
We've gone from radio telescopes to dark matter to funk guitar to the very depths of political commentary in art forms.
Wow, this is.
I'm sorry, guys. I guess.
What an episode!
Wow, this is a varied podcast. We only need to bring up sports,
Sam,
real tennis.
Yes,
Real tennis.
The only
The
sport.
proper way to end the podcast. No, the proper way to end the podcast is thanks for having. Or sorry. Wow,
Thanks for having us,
Yes,
Sam.
thank you.
Yeah, thanks for interviewing us, Sam.
Yeah.
It
Thanks
was
for coming
my
on the
pleasure,
podcast,
dude.
Sam. Do you want to plug your stuff, social media, anything you want to plug?
Yeah, sure. I guess the best way to find me is probably on Twitter at Smorell. That's SMORRELL. I think that's pretty much the best place to find me for the minute. Everything else kind of, all roads lead to Twitter, as it were. So
Indeed.
You can find us on Twitter at From Ignorance. We're also on Facebook. Speaking From Ignorance on Facebook. Like our page. We'll post when new episodes come out. You can listen to new episodes on Anchor FM, Spotify,
Also Google. If you
other podcasting services, which will be available.
It's true.
Sorry, what was that, Jack?
I learned yesterday if you Google speaking from ignorance, Google can just autoplay it, which is great. I don't know
Well, that's
who's
pretty cool.
uploading that.
Oh, because we're on a Google podcast.
awesome.
That might be why.
Oh wait, I had no
And if
idea.
you want some more live updates on like our most recent episodes and stuff, you can also check out our website, sfignorance.github.io. Name pending, trying to migrate that to a new domain name. Thanks again for coming on, Sam.
Oh, it was my pleasure. Thanks for having me.
Thanks to everyone
Yes,
for
thank you.
listening. We'll see you next time.